Awesome. Hopefully what you would have figured out is that actually that was a trick question. Is it the green pen? Is it the red pen? Well, if you're looking at linear velocity that we looked at last year, you would say the red pen is covering a greater distance in the same amount of time, therefore the green pen has a faster linear velocity. And we'll probably be able to see that if we speed it up a little bit. Which pen is most likely to fly off? It would be the green pen because it is travelling a greater distance in the same amount of time. And so I might see if I can get this platform set up in a moment and see if we can get it to fly off. And so now we end up with this little bit of a challenge. How do we define these properties in maybe a different reference frame? And so last year we had VF, VI, A, T, and D as our 5 variables for kinematic equations. I want you to look at your year 13 formula sheet. So here we go. Here's our year 13 formula sheet. Can you find the year 12 equations on this formula sheet? Yeah, well done. So we've got this funny omega f equals omega I plus alpha t, and that looks really similar to something over here, vf equals vi plus at. We've got this funny theta equals omega f plus omega I over t times time. That looks really similar to d equals vi plus vf divided by 2 times time. And so what we're soon going to discover is that actually we're going to change the equations that we had last year, and we're just going to mess up all the symbols. Why? Because now we're no longer talking about objects traveling in a straight line. We're now talking about objects going around in a circle. If we come back to our rotating platform, you'll see here that the green pen is now on a much greater angle spread outwards than the red one. If I was to say every 360 degrees, which pen travels the greatest angular distance? Well, actually, really they're traveling the same amount of angle every time period. So if we said the time to go from here back to here, you'll actually find that it doesn't matter which pen we're talking about, they both take the same amount of time to travel that same angular distance. And so we're now going to come up with these new variables. Okay, so just looking at the notes that I've distributed to you, we're looking at rotational motion. So angular displacement, which is theta, and it has a unit of radians. Now, this is a really interesting kind of idea. So typically, you've probably been only used to working in degrees, and now we're going to mess with that idea a little bit. So angular displacement is a dimensionless ratio between d, the distance traveled around the arc of the circle, and the distance r from the center. So angular displacement is measured in radians because it's dimensionless. And so if we were to unpack that a little bit, if I have a circle and I travelled this far around my circle, so if I travelled the r around my circle, it might look something like that. And so I have r is a length, r is a length, and r is an arc length. And I want to know, well, what is the angle? Well, I define that as 1 radian. Well, then I say, well, how many r's does it take me to go the whole way around the circle? So I've got 1, 2, 3, 4, 5, 6, and a bit. And you might be familiar with that idea, and that idea is pi, isn't it? So circumference equals 2 pi r, or circumference equals pi times diameter. And so, well, what is 2 pi? If you type 2 pi into your calculator, you're going to get that 6.3 or 6.28, whatever it is. And so it's going to take 6 point whatever r's to get the whole way around the circle. And so this is where we get this idea of what is the circumference of a circle. Well, the circumference of a circle is 2 pi lots of radians. And so what is a radian? Well, this r theta thing here is our radian. And so how many degrees is that? Well, it actually works out to be 57-ish degrees, because if you go 360 divided by 2 pi, then you get 57 degrees. And And so angular displacement, how far in an angular sense has it travelled? We're going to use this new unit called radians. So let's have a go at an example. If the radius of the following circle was 3 meters, then we could work out the circumference to be circumference equals 2 pi r. So 2 pi times 3, which is 18.8 meters. If we travelled a quarter of the way around, then I would have travelled, I wouldn't have travelled 2 pi around, I would have travelled a quarter of 2 pi, which is really pi divided by 2, or as it says here, 2 pi over 4. And so that would give me 4.7 meters. That's probably fairly trivial, that example. It's kind of year 10 maths really, but it's going to be able to build to what we're looking at. So a roundabout, something similar to what we've just been interacting with, has a radius of 1.2 meters and has made 6.5 revolutions. What is the angular displacement? So if every revolution is 2 pi, that's going to be 6.5 lots of 2 pi. And so we're getting 40.8 radians. So radians is a unit, even though it's not really a unit. So radians is dimensionless in that it's not meters or kilometers or hertz or whatever, but we still add it just for convention's sake. So what distance did it travel? And so here we've got our equation at the top. Theta equals d over r. And so we're going to look at that, d equals r theta, and we get about 50 meters. Cool. We're now going to look at what is angular velocity. So we've had velocity in a straight line. So velocity in a straight line, translational motion, is distance divided by time. Instead of what linear distance is traveled in a period, it is how many revolutions or parts of a revolution of a circle that it's traveled through. So if it's traveled 1 revolution, then it's traveled 2 pi radians, or 360 degrees. So 360 degrees and 2 pi radians are equatable. They're the same thing. So if you travel 4 pi, then you've gone around once, twice. And if I do that in 0.6 seconds, well, then I've done 4 pi divided by 0.6, and that gives you 20.9 radians. We've covered about 4 pages of SciPad now. That's great. Now we're going to look at angular acceleration. So how do we make things go faster? Well, you have to apply a force. No, you have to apply a torque to make things go faster. And so we're seeing angular acceleration is very similar to linear acceleration, velocity over time, except instead of linear velocity, it's now going to be angular velocity, or change in angular velocity over time. And so now we have 4 kinematic equations that are basically identical to what we did last year, except instead of in a straight line, we're now looking in a rotational sense.